What is stoichiometry? As I've said, guys, it is the backbone of chemistry. It's very, very important to us. Basically, what it is, this is kind of on page 1. You may want to jot this down. It's the relationships or different mass relationships of reactants and products within a reaction. So any lab that you go to, so when I was working at UNCG, or when I worked at Kodak, or if you were to go to Procter & Gamble or Syngenta or any other lab in the area, guys, where they're doing something related to reactions, trying to produce something, all right, they're using stoichiometry on a daily basis. All right, and what it does is this allows us to look at, like it says, the mass relationship between products and reactants. So companies are trying to produce a certain amount of product. All right, so if you go to Procter & Gamble, what's one thing that Procter & Gamble makes? Does anybody know anything they make?
Eggs.
Eggs, not eggs. Good guess. All right. Something you guys probably use every day, I hope. Toothpaste. All right. Shampoo. I think they do make shampoo and stuff as well. But guys, toothpaste or whatever it is, a product like that, they make a lot of personal care products. Let's say they need to make X number of pounds or kilograms of toothpaste for a shipment to go out. All right. So okay, here it is. They look at the reaction that goes along the process of how to make the product that they're trying to, whether it's toothpaste or shampoo or whatever, okay, and they're going to put all the chemicals together. Well, if you don't have a plan, you're kind of shooting in the dark. It's what they call garbage can chemistry, all right, where it's not very efficient and you're throwing away a lot of money. If you understand the chemistry behind it and the reactions that are involved, and you know how much you want to make, how much you're going to sell, you can start with your product. I need 1,500 kilograms of toothpaste. So then they can start, or to figure out how much they need to start with, they can then back calculate from grams. Can we compare grams of one substance to grams of another substance? No. What can we compare? You just got a test back on it. Moles, right? So they'll go from grams to moles, and they can go from moles of one thing to moles of another. They can figure out how much starting material they actually need so they're not wasting anything. Because all extra material that isn't reacted, they've got to throw away, and they're losing money. Do you think companies want to lose money? Absolutely not. So it's all about the money, guys, and that's what stoichiometry allows us to do, is to figure out how much you need of one substance to then predict or make however much you want in the end to sell or to use for something else. All right, so this is why it's so important for us. Okay, so the first thing that we're going to talk about, guys, are these things called mole ratios. So before you write anything down, let's just talk for a minute about this term, ratio. We've talked about it before. We've used them before. What is a ratio? One word is all you need to use to define what a ratio is. And don't say fraction. I know we use fractions, guys, in mathematical processes when we do the math with it, but what is a ratio? That's the most basic term that we've talked about. Tyler? It can be a proportion. Another word, though, that I'm looking for, something else we've talked about. It is a proportion because we are talking about how they're related to one another, but it's really just a what? What? Louder? It's a comparison, guys. You're comparing two different things together. So every conversion factor that we've ever written is just a ratio. Okay? Where we said 1 kilometer equals how many meters? Ooh, a little review there. Kilo means what? 1,000. All right, so 1,000. Good news is, guys, we're not using the metric system here in this unit. Okay? But we've done that before. So now, this thing, jot this down. If you don't have it in your notes, guys, just write ratio and then comparison, because I'm going to drive this home in this unit. That if you don't remember, there's one thing you remember from this course, is that a ratio just means a comparison. You're comparing two different things together. So now when we talk about a mole ratio, what do you think we're going to compare, guys? What? Yeah, moles. Moles of different substances. All right, so we have looked at moles of different substances already. That was the unit that we did before break, which was on reactions. So mole ratio, guys, is determined from the balanced equation. Jot yourself a note off to the side. Do not assume your reaction is balanced. Okay? Do not assume that if I give you a reaction in a problem, that it's balanced. Okay? Most of the time, it's not going to be balanced. I'm not going to do the work for you guys. You need to be able to balance equations like we learned before break. Okay? So do not assume that it is already balanced. If you don't have a balanced equation right from the start, everything you're doing is wrong. All right? It's that important. So, here's our example of an equation. Okay? Jot this reaction down in your notes right there in the spot, or you already have it. Box it or highlight it. Something that's on your notes, okay? Either box the reaction that's there or highlight it so that it stands out, because this is going to be the reaction we're going to use through all of our examples over the next 3 days. All right, so what we're going to do here today, kind of the first thing, is we're going to write mole ratios. What's a ratio again? It's a comparison. So we're going to compare the different moles. Well, in order to do that, we've got to know, we've got to remember what from a reaction tells me about moles. What in the reaction tells me about the moles of each piece? The coefficient, folks. The coefficients tell me the number of moles. What do subscripts tell me? The number of atoms. Okay, which those two are related to moles. Okay, but the coefficients are what I'm going to be interested in for my mole ratio. All right. The coefficients we know are the big numbers out in front. So, to write a mole ratio, guys, something that may help some of you is to draw some lines. So a ratio we said is a comparison. We're going to compare the moles of all reactants to all the products. We're going to compare all reactants to all reactants and all products to all products. So where are reactants in a reaction as a review? If I look at that reaction there, where are my reactants? On the what side? The left side, right? Because the reactants react together to produce what? Products, which are on the right side. All right? So, what you can do, guys, is to draw lines. You want to find every combination between each substance. So, Al2O3, prize question, if you can tell me the correct name of that compound, raising your hand. Aluminum oxide, it's the one we just talked about with our test. So aluminum oxide, guys, here we go. Aluminum oxide, we're going to have to compare it to aluminum. We're also going to have to compare it to oxygen. Is that every comparison that this reaction shows me? Is there every possible comparison? No, because there's one more. What one? Aluminum to oxygen. So guys, by drawing lines. Now the purpose of me drawing the lines here, you're not going to have to do this. It may help you, so you make sure you know you write down every ratio possible. Okay? But it's just to show you that all the different combinations that you could have. Excuse me. So now we're going to start writing those down. So a mole ratio, we're going to compare those. And to do that, we're just going to write down what we have with it. I don't know where that came from. All right, so first one, I'm going to start with how many moles of aluminum oxide I have. So I have 2 moles of Al2O3. I'm going to compare that to one of my products. Does it matter which one I do first? No. Which one do you want to do first? All right, 4 moles of aluminum. So how do we show a ratio, guys, mathematically? Fraction. So that's how we're going to do it. 2 moles of aluminum oxide for every, will produce, 4 moles of aluminum. So I'm going to cross out that first line that I drew in because I've already talked about that comparison. What's another one? Move on to the next one. So my next line. My next line is still 2 moles of aluminum oxide compared with how many moles of oxygen? 3. That line's gone. And then I have one more that I could have as well, which would be 4 moles of aluminum and 3 moles of oxygen. Does everybody see what I've done so far? Is this anything crazy complicated? Yes? No? Something? A head nod? Something, folks? Easy, right? Don't make it harder than it needs to be. Now let me ask you this. Are these the only possible combinations that I could have in this reaction? Who say yes? Give me a show of hands, guys. I need some. Why aren't these the only three combinations? Because what could I do with every single one of these fractions? Not break them down. I could. Not simplify. I mean, I could. I could what? I could flip them, folks. I could flip them to then where I have 4 moles of aluminum over 2 moles of aluminum oxide. I could have 3 moles of oxygen here. I could have 2 moles of aluminum oxide. And I could have 3 moles of oxygen and then 4 moles of aluminum. Now, are they similar, the ones that I flipped? Absolutely, guys. Do we know which one we're going to need right now for a problem? No. But we've seen conversion factors already, guys. If you don't have all 6, I'm not going to be worried about that. If you had the 3 different ones, that's what I'm concerned about. There are 3 what I call unique ratios or comparisons, meaning where you have these 2 compared together, these 2 compared together, and then these ones compared. Whether you have them on the top or the bottom, guys, that's going to be determined by what? What do you think is going to determine which is on the top and the bottom? What I am given to start with, guys. Like every other conversion problem we've ever done this year, what you start with is what's going to determine which is on the top and the bottom. Because we always let our units do what? Drive our math, okay? So you're probably, who's confused with why we're going to use these? Okay? It's okay to say that. Who's confused with how we get these, though? We good with how we get them? We look at the coefficients? All right? We're taking it piece by piece. So here we go. I want you guys to write this reaction down in the space that is there on page 1. Okay? Don't worry about the textbook problems yet. I want you to write this one down, and I want you guys to go through and write the unique mole ratios for this reaction. The unique ones. I'll give you a hint. There's 3. So one that we could have is 2 moles of HGO over 2 moles of Hg. Absolutely. There's one. Who can give me another one? Anna. Absolutely. Who can give me the last one? Darius.
2 moles of Hg over 1 mole of O2.
Absolutely. So folks, if you had a different one than those 3, okay, but it was flipped, you had pretty much the same one. Yes, they're technically a different comparison, a different ratio, but again, we haven't applied this to any problem yet, which is where we're going to get We're about to get into, I mean. Okay? This is what you're looking at. It's just comparing the different substances to one another. Okay? Any questions on this problem? Easy? Pretty basic? Okay? So when you have a question like this, when we get into more complex stuff over the next couple of days, when we come back to a problem, so when I say write down the mole ratios, everybody's like, well, what's a mole ratio? Guys, it's just a comparison. Okay? Don't make it harder than it needs to be. Now, why do you think we might be learning about these mole ratios, these comparisons? When have we ever done any ratio before, guys, or any conversion factor? What have we gone to do from there? We've done a what? We've used a what chart? A T-chart, right? So we're going to convert, guys. What the mole ratios allow us to do, they allow us to go from one substance to a different substance. So by us looking at a reaction, at the reactants to the products, we can then convert by their number of moles, how they're related to one another, because we can compare moles of one to moles of another. We can then go between substances. We can't go from grams to grams, right? Because each element on the periodic table has different mass. We have to look at their moles. So here we go. This is what we're going to start doing, guys. This is on page 2 of your notes. Tomorrow, we will start to make a foldable. It's going to be a guide for us, all right, that will allow us, that will make it easier to keep all the different types together. So this is our type 1 stoichiometry problem. So again, it's on page 2 off to the right-hand side of that front page. What I want you guys to do is to rewrite this reaction right below where it says, you see that moles given and that T-chart that's listed there? I want you guys to write this reaction somewhere around there, a little bit bigger, because this is what we're going to use in the practice problem that we're about to get into. Here we go. The process you want to think about, guys, is given versus unknown when we talk about word problems. All right? So here we go. It says, this is what we call a mole-to-mole problem. This is the simplest of the 4 types. It's a one-step problem. So where it says mole-to-mole, I'm going to write 1 step in my notes to remind myself this is going to be the simplest. Okay, we're going to need 1 conversion factor here. So it says using that reaction, aluminum oxide. What type of reaction is that? Just for review. What's that? Decomposition. How many knows decomposition? It's breaking down. You got 1 reactant and multiple products. So using that decomposition of aluminum oxide, how many moles of aluminum can be produced from 13 moles of aluminum oxide? So what we want to do, what we're going to get in the habit of, is writing down my given and my wanted. And I'm actually going to use 2 different colors here to just keep them separated. You can if you want to, or you can use highlighters, whatever you want. You don't have to use anything, but as we start, it might be a little bit easier to see the process if you use 2 different colors. So first things first, it says how many moles. So how many moles of aluminum can be produced from 13 moles of aluminum oxide? What's my given and what's my wanted here? What's my wanted first? What am I trying to get to? Right. It's not just aluminum, right? Or it's not just moles. It's moles of aluminum, guys. You have to have both pieces in your unit. Okay? Because you're not just staying with one substance anymore. And eventually, by the end of this unit, we're not going to be staying with the same unit either. All right? So we have how many moles of aluminum? And then what's my given? "13 moles of aluminum oxide." Okay? So this is where it's very important, guys, that you are organized, because we have 2 different substances we're dealing with, and we're eventually going to have 2 different units. We're going to have grams in there or moles. And that kind of tells us and gives us a clue as to how many steps we're going to need to solve our problem. So this one's a basic one. It's mole to mole. It's a 1-step problem. So I'm going to set up my T-chart, just like I always have. What's the first thing I write down within my T-chart? What I'm given. So in this case, 13 moles of aluminum oxide. What goes underneath that first fraction? Always O1, right? Has anything changed up until this point for us? No, nothing has changed. This is a process we've already been using all throughout the year. We've done it extensively. All right, so it's nothing brand new. Okay? So, what am I trying to get to in the end? Which is what? Moles of aluminum. So there's my wanted. So that means I don't want to stay with moles of aluminum oxide. So where does that unit, moles of aluminum oxide, have to go in my next fraction and cancel out? On the bottom. And then what's my unit going to be on top? Moles of aluminum. Again, I'll ask the question, have we done anything really groundbreaking or brand new? No, guys, we've done this process time and time again. All we're doing is crossing out, canceling out our first unit, and getting to our new one. Now, the new piece for us is this next step. So within this fraction right here, this is our conversion factor. Okay, we've got to figure out the numbers. Okay, up until this point, we had our conversion factors written off there. Well, we don't have that here. What do you think we're going to use? We have moles of one substance and moles of a different substance. What do you think we're going to use as our conversion factor? The what? The what? Somebody said it, I think. The mole ratio, guys, what we were just learning about. This is where that mole ratio comes into play. It allows us to convert between 2 different substances. I'm going to jot that down. You may want to jot it down in your notes as well. It allows us to convert between 2 substances. It allows us to convert between 2 substances. Where do we get the mole ratio from? Where do we get the mole ratio from? The reaction. So guys, we have aluminum What's the coefficient for aluminum? Nope. 4. Aluminum is 4. What's the coefficient for aluminum oxide? That's a 2. There it is, guys. There's our problem. For us to go from one substance to another, all we need is the mole ratio. So now we can do the math. Can we simplify this? We don't even need calculators for this problem. What's 4 divided by 2? What's 2 times 13? So guys, in the end, we end up with 26 moles of aluminum. So let's talk about what this means for us. This problem is saying, if I start with 13 moles of aluminum oxide, based on my reaction I have here, I could produce, at most, 26 moles of aluminum. So if I had, again, 13 moles of that aluminum oxide to start with, I could produce up to 26 moles of aluminum. This is what stoichiometry allows us to do, is if we have a starting amount, how much of something can I produce? Is this, again, anything super groundbreaking new for us here, guys, in terms of math? We've done this math over and over. The new piece is this mole ratio piece and where that comes from. Let's try another example here together. This is not in your notes. All right, so at the bottom where you have space, you're going to write this in. Here's our new reaction. Go ahead and jot that down. So again, get in the habit of writing down given and wanted to start the problem, and then start identifying your pieces. So it says, how many moles of hydrogen are produced from the reaction of 3 moles of zinc with an excess of HCl? So what's my given? I've got 3 moles of zinc. What's my wanted? What am I trying to get to? How many moles of hydrogen? Why do we have to write hydrogen with an H2 there? Brinkel-off, which means it's a diatomic. When they're by themselves, they exist in pairs of 2. Okay, so we have 3 moles of zinc is what we're starting with. Different type of reaction. Who can tell me what type of reaction this is? It's not a decomposition. It's a what? Not a double replacement. Single replacement, right? Because we got a single element right there coming into a compound, and then a new element's produced. So, how do we do this? Always start off by writing start with my given, right? So my T-chart's right here. So I have, in my given, I've got 3 moles of zinc. What goes on the bottom of that first fraction always? A 1 is a placeholder. And I'm trying to get to what? Moles of H2 in the end. Okay? Where does zinc have to go? On the bottom, because we're trying to get rid of moles of zinc. On the top, my unit would be moles of H2. Now, to go from one substance to another, guys, what do I have to use? My mole ratio. So this is where we're gonna look up at the top. If there's no number written there, what's it assumed to be?
1.
A 1. So for zinc, what's my mole? How many moles of zinc do I have? 1. For hydrogen, how many moles do I have? 1. Oh, that makes my math very easy. If I have 3 moles of zinc, how many moles of hydrogen will be produced? That's it, folks. That's all we have to do. Let's talk about this term, excess of HCl. What do you think that means? Does that have any impact on our reaction? What we're trying to do? What does excess mean? What does it mean? Leftover or extra? We will talk about excess reagent or excess reactant, guys, later on toward the end of the unit. But for now, if you see that there, that means we're not going to worry about whatever substance is in excess. Okay? We're not going to worry about that. It has no impact on the problem at hand that we're looking at. Questions on this problem? Your homework tonight is page 8, numbers 1 through 5 in your packet. You also have vocab due on Monday. There's only 8 terms. You could probably get that done tonight.